kind of a random question. So, in like the lesson, there were like two sets of like x and y equations, and when we're solving them, we only use the first one. What was the second one?
So you're talking in the second lesson here, right? Let me go back and double check to make sure I'm sure which set that I'm talking about, because I don't want to give you the wrong answer here. So there is the set. I only see one set of xy equations. I see a set of vx, vy equations. So you would use those if you're trying to solve for a velocity, as opposed to like a how far or how high question.
Okay.
So if we're asking like how fast, that would be a time to consider using those, unless you're looking just for the initial velocity.
All right.
But if you're looking at like some instantaneous velocity, that's when you would use those.
Okay.
You know, like you fired, some cannonball, and after 3 seconds, how fast is it going? That would be a time to be interested in those equations, kind of thing. You know what I mean?
Yeah.
Does that feel okay?
Yes.
And yeah, in the examples, certainly we saw nothing where we needed to do we used anything other than distances, right? And I can't even remember, it's been a while since I've looked at this homework, but I feel like the same thing happened here, right? Everything, we used just distances in all the homework problems too. Is that correct? Is that what you saw anyway, Sam? Okay. Yeah, that sounds right. Okay, Kara. 48. Sure hope so. So it says Nick hits golf balls off a practice tee with an initial velocity of 80 feet per second. With 4 different clubs. How far down the fairway does the ball hit the ground if it comes off the club, making the specified angle with the ground? So how far? That's looking for x. And then I'm just going to do like the first one with the first angle because they're kind of all the same, if that's okay with you. Okay. So I know x is equal to the magnitude of v cosine theta times t, and y is equal to negative 16t squared plus the magnitude of v times sine theta times t plus s naught. Okay? So what my plan is going to be is I'm going to solve the y equation for t and then use that solution to plug into the x equation to figure out how far. So here it doesn't tell me the height of my golf tee. I'm going to assume they're just hitting the ball off the ground. So for the ball to go up in the air and it's going to land back on the ground. So I'm interested in when the height of the ball is 0. So this is, and I guess I could write a plus 0 at the end, but it doesn't really need it. This is a quadratic equation that I need to solve. It's actually a really easy quadratic because there's no constant term on it. So I can just solve this by factoring. There's a greatest common factor of t that I can take out. And then when I apply the zero product property, I can set each of the factors equal to 0, and then solve. And I guess I could now plug that solution into my equation for x. And when I get that, I get 951.4 feet. And if you think about this in golf terms, that's like 300 something yards, which is far, but still like feasible. Like a human being can do that. You have to be pretty good to do that, but like that's a feasible distance for a golf ball to travel. So I feel pretty good about that. Does that feel okay?
Yeah.
Let me just double check my answer key here to make sure that that is what I'm supposed to be getting. Yep. Other questions from this assignment? Maddie? 44. Says, stop talking, please. Matt hits a baseball when it's 3 feet above the ground with initial velocity of 115 feet per second. And the ball leaves at an angle of 41 degrees and heads towards a 20-foot fence 385 feet away. Says, write the parametric equations to model the flight of the ball. Okay, so x is going to equal the initial velocity times cosine of theta times t. And y is going to equal negative 16t squared plus the initial velocity times sine theta times t plus the initial height. In part B, it says, if no fence or other obstacles were present, find the distance the ball would travel when it first hits the ground. So what I'm going to do there for that is I'm going to take the equation for y, solve that to find the value for t, and then plug t into the x equation to find the how far. So the ball's going to hit the ground means its height would be 0. So that's a quadratic equation. So I'm going to solve it using or with the quadratic formula. And if you guys still have your quadratic program in your calculator, this would be a good use for it. If you don't, you could reprogram it. Would not be a waste of your time. Yes. Yes. So I get negative 0.7, which is clearly not the one that I'm looking for. But remember, this is a plus or minus, so let's try the minus. And there I get 9.50 or 9.51. So that's the one that I need. And then I'm going to plug that into the x equation. To get 825 feet. That seems too big. What happened here? My value for t was wrong. Let me look at what I did here. Well, Maddie, I don't see the mistake right away, but that's clearly not the right answer. Oh, shoot. I see it. Times 2. There we go. That's better. I forgot the 2 here. Yeah.
Why don't we graph this instead of the formula?
Well, we're looking for the exact value. What was that? 421, 6. Maddie, are you okay there? Okay. And then part C says, stop talking, please. Will the ball clear the fence? If so, by how many feet? If not, will the ball be catchable, i.e. less than 10 feet from the ground? All right. So what I'm going to do now is I'm going to take the x equation and solve it for 385. And I'm going to plug that into the y equation for t to see how high the ball is going to be at that distance. Because if the ball is over 20 feet at that distance, then it's going to clear the fence. If it's less than that, it's not. Okay with that, Maddie? Okay. So 385 divided by 115, 115 cosine 41. So I have negative 16 times that answer squared plus 115 times sine 41 times that answer plus 3. So that's bigger than 20 feet, so it'll clear the fence. You should be in degree mode. Are you in radian mode? Okay. Shouldn't matter beyond that. That would be been the only mode thing that would have made an impact on what was going on. Whether it was function or parametric wouldn't have mattered there. maybe let's talk a little later, and we'll sit down and I'll watch what you're doing on your calculator, and I can give you some more specific feedback. But it sounds like you're doing the right things. But we'll look at what you did, and we'll figure it out, okay? Last call on questions here. Bridget? 24. Sure. All right. So the domain, I'm going to be looking at the x equation. And there's 3 values of t that I'm going to be concerned about on this x equation. I'm going to be concerned about both endpoints. And since this equation here is quadratic, I'm going to be concerned about where the vertex is as well. So if I look at this equation and I think about this as a function of t, the vertex of this would occur when t is equal to 0, right? Remember, for I can find the x-coordinate of the vertex by doing negative b over 2a. In this case, the b value is 0, so the vertex has the x-coordinate 0. So I'm going to be interested in those 3 values of t. Okay with that? Okay, so that's going to be, well, I guess I'll use my calculator. 3 times negative 8 squared plus 2. And then 3 times negative 3 squared plus 2. And then 3 times 0 squared plus 2. Okay? So my domain then is going to be the set of x's from the smallest to the biggest. Okay with that, Bridge? Okay. To do the range, I'm going to be looking at the y equals equation. This is a linear equation, so this is much easier. All I care about are the 2 n in my my interval for the parameter. So I get negative 4 and negative 3 over 2. So my range is the set of y's from negative 4 to negative 3 over 2. And you didn't care about eliminating the parameter, right? You just asked about the domain and range part. Okay. So I did skip part of this problem because that wasn't what we were asking about. Just so everybody following along knows that there was more to do here, but we skipped it because we didn't care about it. It wasn't part of the individual question that Bridget was asking. Does that feel okay there? So that's how it basically boils down to, is just if you have linear, all we care about are the endpoints. If it's got other maxes and mins in there other than the endpoints, if it's not increasing the whole time or decreasing the whole time, then we have to worry about where those individual extrema are. In the case of a quadratic, it's pretty easy to find the other extrema because it's the vertex and it's easy to find that value for t that would give us the vertex because we have a formula to do it. If it was like a degree 5 polynomial, then it's way harder and beyond the scope of this kind of a class. Yeah, if you had calculus, it wouldn't be bad, but we don't have calculus, so. Okay. All right. Shall we move on? Anybody else? Okay. Okay, so the next thing we're going to talk about is the polar coordinate system. So in the previous sections, we had talked about parametric functions, and parametric functions are still creating a graph on the same xy axis. Can we stop talking, please? Okay, so the parametric function is still graphing on the same xy axis, right? We're using a parameter to generate our x and y coordinates separately, but we're still graphing in the same fashion that we would before, right? We're plotting our x's and y's. A polar coordinate system is going to be different. So this is a different way of kind of representing information. And this is going to tie back into the vector stuff that we had talked about before, but not like overly so. And I'm going to just abbreviate the polar coordinate system as just PCS, just because I'm going to have to write that a couple of times, and I just don't, that's a lot of letters. So we say a point in the polar coordinate system is defined by the general form r comma theta, where r is the point's distance from the origin, and theta is the measure of the standard form angle whose terminal side intersects that point. What does this sound a lot like? When you read this definition, what does this sound a lot like? Sounds like the magnitude and direction definition of a vector, right? Where we defined a vector with a magnitude and a direction. This is very much the same idea here. So, what does the polar coordinate system look like when you look at it? Let's take one pass. Drop that in real quick.
I know it.
So this is what the polar coordinate axes look like. So notice that just like the xy axis, I still have like an x and y axis in here. Everybody notice this? So they still have that set of perpendicular axes, just like the x and y axis. But we also have these concentric circles, right? So, and then we have these other diagonal lines like intersecting these concentric circles. So each of these angles, each of these wedges are 30 degrees, or pi over 6 radians. Is everybody okay with that idea? Okay, so each of those concentric circles is 30 degrees or pi over 6. So if you look at each of these circles, this first circle is like our standard unit circle, right? The radius there is 1. Can we stop talking, please? I didn't realize we all knew how to do this already. The next circle is like a 2-unit circle. So the radius there would be 2 instead of 1. This next circle is like a 3-unit circle. So there the radius is 3 instead of 1. And it continues going out, continuing that same pattern. So each circle is 1 more radius longer. Everybody okay with that? So when we talk about the polar coordinate system, the point here at the center, what we would call the origin in the Cartesian coordinate system, is called the pole in the polar coordinate system. and FYI, sometimes we refer to the Cartesian coordinate system as a rectangular coordinate system, because to graph a point xy, we're basically just drawing a rectangle, as opposed to the polar coordinate system where to graph a point we need a circle. So there, just as a piece of vocab, if you see that anywhere, that's what we're referring to, is just rectangular coordinate system is the same as the Cartesian coordinate system, the xy axis that we've dealt with before. So to be able to graph something on the polar coordinate system, we need to know the magnitude and direction, just like when we graphed a vector. So the r is the magnitude, and the direction is that angle theta. And we don't really need to find the specific xy point. That piece of information, the magnitude and the direction, perfectly describe where that point should lie. So let me just erase all these marks here, and we'll do some examples. So let's say I wanted to graph the point 3, 120. So the first thing is I'm going to figure out which of these diagonal lines, or which one of the straight lines, I guess, it could be not, it doesn't necessarily have to be one of the diagonal ones. It could be a perpendicular or a vertical or horizontal line. But which one of the straight lines 120 degrees corresponds to? So remember, here we're at 0, and then it's 30, 60, 90, and so this line here is the 120 line. Everybody okay with that? You see how I counted over to find that? Okay, and now to figure out a magnitude of 3, I'm going to count 3 circles along that line. So 1, 2, 3 is where my point would go. Is everybody okay there? Guess I probably should have drawn that in red, huh? So it matched 1, 2. Everybody's okay there? Should we do another? Yes. So -2 and pi over 3. So remember, each of these straight lines is 30 degrees, or pi over 6. So pi over 3 is 2/6, right? Everybody's okay? Or 2 pi over 3? Or I'm sorry, 2 pi over 6, excuse me. Yeah. So which of these straight lines am I interested in? So here's pi over 3. There's 2 pi over 3, so I'm interested in this one here. Everybody's okay there? And then I need to go -2. So which direction am I going to be going? In the negative direction, so kind of to the left, 2 circles down. So that makes my point here. Is everybody okay there? Okay. The next one, -1, -100. first thing we do is figure out the line that the negative 100 degrees lies on. So because it's negative, which way am I rotating along my axis? Clockwise. So we'd be at like negative 30, negative 60, negative 90. And then like 10 degrees more is going to be something that kind of comes in like that. Pardon my not straight line. But I'm just estimating, trying to pick, that's maybe not that great of an estimate, trying to pick about a third of that thing. Also not a great estimate. I can do this, guys. It's hard to do it. All right, that's good enough. So there's about 100, negative 100 degrees. Is everybody okay with that? So I had to estimate a little bit. Basically, I wanted like a third of the wedge, because if each wedge is 30 degrees, 10 degrees more is going to be a third of that. And then I'm going and finding my point on the one circle, or the unit circle, in the negative direction. Oh no, wait a minute. Oh shoot. All right, I lied. Hold on a second. So here we're negative 100, right, is down here. But now we're going up because we're going opposite direction, yes. Yeah, so that is a little sneaky. Brockton. Okay, so yes. So the negative, let me grab a different color here for this. So negative 100 is really this part here, right? But I'm going the opposite end of this because I'm going negative 1 is going on the opposite end. So this is negative 100 here, this line. But I'm going the opposite direction along that line, so I extend back and graph up on the blue part rather than the purple part there. Does that make more sense? It's maybe a better description of what I was doing there. Sometimes you just trip over your own words. So, the annoying part here is, because of the way we've defined what negative distance means, for example, is negative 2, pi over 3 the only way to represent that point there in blue? No. Right? How else could we describe that point in blue? So I could call it also positive 2 and then pi over 3 plus 180 degrees. Because remember, how far is this distance going to be? 180 degrees, right? That's half of a circle. Or in other words, 2, 4 pi over 3. Everybody's okay there? So this point and this point are representing the same thing, right? So if I change the sign on the magnitude and I add 180 degrees to the angle, I'm going to get another point that's in the same location. Right? Is that the only way I can do that? What else could I do? So I could choose a negative angle. Sure. So I could have subtracted 180 as well as added. Absolutely. That would be fine. Is there a way to leave the magnitude the same? So can I write it so the magnitude is still -2, but I give a different angle measure and still end up in the same place? If I did that, what is going to be 2 pi plus pi over 3? What do we call those angles? Pi over 3 and pi over 3 plus 2 pi. We have a term for those angles. It starts with a C. Coterminal, right? Because they're really in the same location, because we've just gone 360 degrees around and ended up back where we started. Okay, so let's kind of package these observations together into a definition. Okay? Okay, so again, I wrote this two versions of the same definition, one in degrees and one in radians. So this first one is like our coterminal stuff, and this is the different end but opposite direction. You know what I mean by that? I don't know how best to phrase that. Worth pointing out here that this parenthesis is not just for show. We got to really do that first. You can't just simplify that down and say, oh, it's just theta plus 3 pi n. Pi and 2 pi n are not like terms. You can't just add those guys together because of the variable n there. You literally have to add 180 first and then find the coterminal part to it, or it's not going to work out. So don't try to simplify that formula down. Let's do an example, and then we'll stop here for today. Sound good? So, suppose we want to find all the polar coordinates that coincide with the point 8, 5 pi over 6. Well, I'm just going to use my definition from up above. So I have my coterminal stuff. And then I have my opposite end stuff, but I can simplify that down a little bit. What do you think? Not bad. We'll do some more on this tomorrow, but there's still more to do.